Okay, guys, we started off probability by doing a set of experiments with coin tosses and rolling number cubes. Unfortunately, that means we didn't do the vocab. So we've got to go back a little bit and talk about some of the vocabulary that we need to know. Our first vocabulary word is sample space. Now, this is all the possible outcomes. Now, this is not all of the possible outcomes any time, any place in a universe. This is all of the mathematical possible outcomes, such as on a number cube. It has a sample space of 1, 2, 3, 4, 5, or 6. There is no 0. There is no 1.5. There is no 7 on a 6-sided number cube. Okay, so that is sample space. We have independent events, which is when the outcome of one event has no impact on the outcome of another event. So if I roll a die and get a number and draw a playing card, the number I roll on the die has no impact on what card I draw from that card deck. But I can have dependent events, which is where the outcome of the first event has an impact on the outcome of the second event, or even third or fourth, going on like that. For instance, if I draw a card from a regular deck of cards, 52 cards, then I set that aside, and I draw another card from that same deck. I started off with 52, now I have 51. I have changed the sample space. Okay, that makes that second card pool a dependent event because the first card pool impacts the outcome of the second card pool because I changed the number of cards I had to choose from. Okay. Now we can have compound events, which is when two events occur at the same time or very nearly the same time. Okay, I don't have to try and juggle drawing a card and rolling a dice, but I need to draw a card and roll the die. I can't draw a card today and roll a die tomorrow and have those be compound events. Right? They need to happen at the same time or very close to the same time. Right? We can have overlapping events where the outcomes have some shared characteristics. If you're asked about rolling a number over 3, so a 4, 5, or 6 on a regular 6-sided number cube, and the probability of rolling an even number, 2, 4, or 6 on a 6-sided number cube, then you have 4 and 6 in both outcomes as possibilities. We can see that visually in the Venn diagram. Okay? So this circle is the probability of rolling a number over 3. 4, 5, and 6 are my possible outcomes. And then this circle is rolling an even number, 2, 4, or 6. 4 and 6 are overlapping in this Venn diagram. It's true of both of those outcomes. Now we can call that 4 and 6 are mutually inclusive. They are included on both. But we can see also that if I have a coin toss, I either land on heads or I land on tails. I don't land a little bit on heads or somewhat on tails. It's heads or tails. And if I land on heads, then tails is out of the question. And if I land on tails, then heads is out of the question. We call these mutually exclusive. They share nothing in common as outcomes of an event. Okay. Excuse me. So now we're getting into the math part. A new to you word is going to be factorial. It is written as a number followed by an exclamation point. Okay? This is calculated by multiplying the number, and that exclamation point means times all of the other numbers that are less until you get to 1. Right? So 10 factorial, or 10 exclamation point, in actuality is telling me to take 10 times 9 times 8 times 7 times 6, got a little typo there, times 5, times 4, times 3, times 2, times 1. And when I put that into my calculator, I get 3,628,800. I'm going to show you how to do it on the school calculators. You have to input the number, like 10, then go to Menu. You're picking 5 for probability, and factorial is 1. I am selecting that. You can see in my calculator that my cursor is blinking after having entered a exclamation point after that 10. I'm going to hit enter, and there is my 3,628,800 outcomes. Okay, so sometimes our possible outcomes are huge. If I had 10 people in a classroom, there are 3.5, a little more than 3.5 million different ways to put those 10 people in line. Okay, that's a lot. We could be standing in line for a while doing that. But I had to look up how to find the factorial and do it in my yellow calculator, so I wrote it down in our notes so you would have it. Okay. Now, we have two ways other than using the factorial to figure out some possible number of outcomes. We have permutation and we have combination. Permutation is NPR, and we use this where the order of the outcome matters to us, okay? So for example, the order of C, A, and T is not the same as T, A, and C using permutation, okay? We use this if we're trying to figure out how many ways we can award a gold, silver, or bronze medal, or a president, vice president, treasurer. Another example might be whoever name I choose first gets $20, the next person gets 15, the person after that gets 10. I care which number I'm at, okay? Because there is a different status depending on the order of the outcomes, right? And we'll do a problem with that. So it is found in the calculator, again, at Menu, 5 for probability, 2 for permutations, and we enter it as N, R, where N is the pool of competitors, and R is the number of selections that can be made, okay? I could have 10 people running for office, and I could have 3 that'll be selected, president, vice president, and treasurer, and that's how I would use these numbers. Okay. Now then, the next way we can find a number of possible outcomes is through combination. And this is where the order of the outcomes does not matter, okay? Where ordering CAT is the same answer as TAC, okay? And it's used for the same status or the same prize level, okay? So let's consider teams advancing from the round of 8 to the round of 5. It doesn't matter if you advanced first, second, third, fourth, or fifth, as long as you advanced, okay? Or I'm going to pick 3 names, and each person is going to get a $5 prize. I don't care if I'm picked first, second, or third, because the prize is all the same, all right? That's when we use combination, and we find that in our calculator under Menu, 5, 3 for combination, and we're still using the same kind of variables, N for the pool and R for the selection. And let's turn the page and take a look at some of those problems. Okay. Just change pages. All right. Permutation, where we are picky about the order. The order matters. There is a prize for coming in first. Now remember, that factorial symbol is that exclamation point. So I showed you 10 factorial. Let's do a 5 factorial. So that is 5 times 4 times 3 times 2 times 1. 20 times 3 is 60. 60 by 2 is 120. 120 times 1 is 120. Guys, I won't write times 1. It doesn't add any value, okay? I've got limited space. This takes up too much space. It means I have to write something else. It makes my finger hurt. I don't usually write 1 unless we really need it. Okay? So we're using this factorial to determine how many ways I can order these 5 people in a line. Okay? There are 120 ways I can do that. But if I need to go from 5 people and make a selection downwards, I'm going to use permutation if I have differing prizes, gold, silver, bronze. Okay? So here's that NPR, where we are taking the pool as a factorial. Then we're taking the pool minus the selection. We're doing that math. And then we're taking it as a factorial. Okay? So let's look at example 2. There are 8 teams competing in a bobsled skeleton race. Cool. How many different ways can each team finish? Okay? Well, for slot number 1, in the beginning, I have 8 teams competing for that. Once that slot is filled, slot number 2 has 7 teams competing for it. Once that slot is filled, then slot number 3 has 6 teams competing for it. Slot number 4 has 5. Slot number 5 has 4. Slot number 3, okay, 1, 2, 3, 4, 5. Slot number 6, sorry. Slot number 7, slot number 8, 4, 3, 2, and 1. Okay? So that's literally 8 factorial. Okay? And from what we learned about our fundamental counting principle, I am multiplying all of the possible outcomes together in order to find my total outcome. And I'm just going to go ahead and put 8 in my, or 8 factorial in my calculator. I'm going to see what's happening. So 8, menu, 5 probability, 1 factorial, enter, enter. 40,320 different ways that we could organize these 8 teams. Okay? We would be playing musical teams forever. Okay, that's kind of a big mess, right? That's a lot. All right. So let's look at what happens. How many ways can we award a gold, silver, and bronze medal? That means our N, our pool of applicants, are those 8 teams. Our R is 3 because that's the number of things that can be selected as prize winners. Right? And we are using NPR. So my N of 8 as a factorial divided by N8 minus R of 3. Do that first. Make it a factorial. Okay. I'm going to do a little bit of cleanup in here. 8 factorial because I haven't taken any action there. 8 minus 3 is 5 factorial. Okay. Now remember, this factorial is not a variable. It is not an x, it is not a y. It is a shorthand way of saying do a process that looks like this. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 that I don't write, divided by 5 factorial, 5 times 4 times 3 times 2 times the 1 I won't write. 5, 4, 3, and 2, both in the numerator and the denominator, reduce down to 1, giving me 8 times 7 times 6 over 1 equals, I don't know, Miss Hart, 8 times 7 times 6 gives me 336. So there are 336 different ways that these 8 teams might win these 3 medals. Okay? Example 3. You are burning a CD demo for your band. Your band has 12 songs stored on your computer, but room enough on the demo for only 4 songs. How many different orders can you burn the 4 songs onto the demo? Okay, this problem tripped me up the first time. It gave me a lot of information I didn't need. Let's look at the question asked. How many different orders can you burn the 4 songs onto the demo? So the 12 songs, you guys have already pared down to 4 as a band, okay? Because you've only got 4 really great songs. And you want to burn those and send them to the demo. Now you've got to argue which of the 4 is going to come first, second, third, and fourth on the demo. What song is going to be heard first? Okay, what song is going to be heard second? Maybe you kind of know that the third and fourth song might not really even get a listen if they don't like the first 2. Okay? That's what you're going to argue about. All right, but the way we do that is we want to order 4 songs. How many different arguments can we make? Okay, 4 times 3 times 2 times 1, and again, I don't normally write that. 4 times 3 is 12, times 2 is 24. You're going to have 24 different ways that you could put these 4 songs on that demo tape, CD. Showing my age. Okay. So that is the basics of permutation. Continuing on, we have that combination. Okay. Combinations, we don't care about the order, okay? Because we aren't doing gold, silver, bronze. We're just doing you advance to the next round. There's no better prize for being first versus being 8th, whatever number of prizes are awarded. Okay? So in this case, CAT is not the same, or is the same, pardon, is the same as TCA. Okay? Because Carla, Anthony, and Tom, those 3 winning a prize of $5 each is not any different than Tom, Carla, and I forgot who I named with the A, winning a $5 prize each. Okay? I don't care if I got chosen first, second, or third. I don't care about first, third, one. I'm getting my $5. Okay? Don't care if I got it first, got it last, as long as I got the same prize. Okay? And that is how it is different from permutations. Okay? And the formula is different right here. We're dividing by that selection. And what that does is it eliminates the duplicates. Okay. So CAT can be ordered CAT, CTA, ACT, ATC, TCA, TAC, all 6 of those. How do I know? 3 factorial is 3 times 2 times 1. I got an output of 6. I've got 6 different ways. But guys, all of these are the same answer under combination. Under permutation, these are 6 different answers. Okay? Under combinations, those count as 1. All right? So let's take a look. There are 8 teams competing in that bobsled race. Only 6 teams make it to the next round. Okay? Don't care as long as I'm part of that 6, because advancing first versus advancing 6, there's no difference. It's all the same advancement. Okay? This one, our problem is nice to us because it gives us the word combinations. So how many different combinations of teams can make it to the next round? Okay, I'm going to use my combination NCR, where N is those 8 teams, and R is the 6 that I can select. I'm just going to plug it into this equation first. Okay? 8 factorial divided by 6 factorial times N of 8 minus R of 6 times factorial. Okay? I'm going to do a little bit of cleanup. 8 factorial. I haven't done anything with this 6 factorial. 8 minus 6 is 2 factorial. Okay? And what I want you to recognize, guys, is this is not addition. This is not multiplication. Those are factorials. That means I want 6 times 5 times 4 times 3 times 2 times 2 factorial, 2 times 1. Okay? So don't try and combine these. These are not like terms. But I am going to write them out. So 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which I'm not going to bother to write, divided by 6 factorial, 6 times 5 times 4 times 3 times 2. Now 2 factorial times 2 times 1. Okay? How about I mark that in another color? Okay. This is the 6 factorial. This is the 2 factorial. Okay? And now I'm going to go through and do 6 and 5 and 4 and 3 and 2, and all of those reduce down to 1, giving me 8 times 7 divided by 2, or 56 divided by 2. And when I put that into my calculator, I get a final answer of 28. There are 28 different ways that these 8 teams can advance to the next round. Okay? So mix and match those 8 teams, with 6 being the selected number down. Okay? Part B says, well, how many ways can the top 3 be chosen? All right. Remember, though, I've already gone from 8 to 6. So my pool has changed. My N has changed to 6. My selection is 3. But I'm still not told gold, silver, bronze, okay? We're just going to the round of 3, so it doesn't matter whether I advance first, second, or third, because I'm going to compete at this level. I just want to advance. So again, this is a combination because, again, I don't care if I advanced as slot 1, 2, or 3 because it's all the same. Okay? So NCR, again, I'm going to fill it in. I did have a change in my N because I now have 6 teams to select, and I have 3 selection spots. 6 minus 3 as a factorial. Okay? Going to do the exact same thing. I'm going to clean it up a little bit. And 3 factorial. And now I'm going to move it all out, or expand it, that's the word. 6 times 5 times 4 times 3 times 2 times 1, which I'm not going to write, over 3 factorial, 3 times 2 times 1 that I'm not going to write, times 3 to factorial, times 3 times 2 times the 1 I'm not going to write. Right? Let me go ahead and mark that again. This is 3 factorial, and this is 3 factorial. All right, I got a 3 and a 2 that'll automatically reduce down to 1. And so I'm going to go from this spot. 6 times 5 times 4. Come on, little machine. 6 times 5 times 4 gives me 120. And 3 times 2 gives me 6. So 120 divided by 6 leaves me 20. Okay. Of these 6 teams to advance to the final round of 3, there are 20 different configurations I can do without repeating any of them. Okay. Okay, back to our band, where you are burning a CD demo. Your band has 12 songs stored on your computer, but room enough on the demo for only 4 songs. How many different combinations of songs can you put on the demo? Okay, this one asks a slightly different question. You've got a pool of 12 and room for 4. So I'm going to write that down. My pool is 12. My R, or my selection amount, is 4. And the problem gave us the right hint that I'm going to use NCR, or my combination equation. All right, let's do that. N12 factorial divided by R4 factorial times N12 minus R4, close factorial. Do a little bit of cleanup. And 4 factorial, 8 factorial. So 12 times 11 times 10 times 9 times 8. I'm going to do a little thing here because I'm lazy. And I'll show you what I did. And then 4 factorial, 4 times 3 times 2 times 1, which I don't write, times 8 factorial. Okay. Because instead of writing it out and writing this out and going 8, 7, 6, 5, 4, 3, 2, 1, I'm just going to do that. Okay. Because those reduce down to 1. And you know what? I'm too lazy to go ahead and try and figure all of that out. I'm just going to put it in my calculator. 12 times 11 times 10 times 9 gives me 11,880. And my denominator is 4 times 3 times 2, and that gives me 24. So 11880 divided by 24 gives me 495. Whoops. As my final possible outcomes of taking my 12 songs and choosing only 4 of them, okay? Or you and your band are going to have about 500 arguments over which of your songs should be one of the selected 4, okay? On your homework, okay, that is how many ways. Oops, next page. I am going to do number 2, and I'm going to do it out, but first I'm going to make a conjecture, all right? How many different ways can you arrange the numbers A, B, C, and D? Well, I'm thinking that that is 4 factorial. I'm not taking out any of the numbers, okay? I just want to know how many orders can I put them in. Okay. 4 times 3 times 2 times 1. 12 times 4 is 24. That is going to be my conjecture. Now, I can already hear you guys. Prove it, Miss Hart. Okay. A, B, C, D. A, C, D, B. A, D, B, C, A, B, D, C, A, C, B, D, A, D, C, B. That's one set. All right, let's try another set. B, A, C, D, B, A, D, C, B, C, A, D, B, C, D, A, B, D, A, C, B, D, C, A. All right, next set. C, A, B, D, C, A, D, B, C, B, A, D, C, B, D, A, and C, D, A, B, C, D, B, A. Last set. D, A, B, C, D, A, C, B, D, B, A, C, D, B, C, A, D, C, A, B, D, C, B, A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Woohoo! I got 24 possible outcomes. Okay? That took a while, and I'm lazy. I did not enjoy that, and my hands are tired. Okay? Guess what? I like this. This is so much easier. Okay? I don't have to go through all of this. You know, and you get a number starting to get bigger than 4, you're going to be writing forever. Oh my gosh, it's ridiculous. Okay? We like this. It's a very nice shortcut. Okay, so in these boxes, yeah, y'all should all be surprised that you are going to use the letters M, A, T, and H. Thanks, guys.